the last talk of the workshop, and after it, there'll be standard closing remarks and the awards and stuff. But we're happy to have Gil Refael back, and he's going to talk about universal quantum computing with Majoranas. Welcome, Gil.
Thanks. Sorry for being late. There are very few occasions in which I'm not late. Let's see. So where were we? So last time we were talking about how to make Majoranas in topological insulators, right? I promised you how to make Majoranas in wires. Now, I don't really know how to make Majoranas in wires since I'm a theorist, but I can suggest something for experimentalists amongst you. So, the first thing I wanted to say is, yeah, so
there are some experimentalists, like Carl, an experiment.
what?
Nandini was saying there are no experimentalists in the audience. I said at least there's one or two for sure. Sometimes we have more.
So we can still, so we can in principle pretend that all experiments that we dream about exist.
Yeah. Nobody's going to
so-
stop you.
What?
Nobody's going to stop you.
Yeah. All right. So Majorana wires. So the point is that topological insulators were a good inspiration for us to get Majoranas. Not as good as Alexei Kitaev, but still, got us halfway there. And then came the idea to use spin-orbit coupled wires to approximate topological insulator edges, but without the need of the new material science and the new material platform. So there are materials that have strong Rashba interactions, and you can make wires out of them. So examples are indium arsenide, and even better, indium actinolite. And the properties of these wires is that instead of just having electrons that have this Hamiltonian, there's an additional piece which has a spin-orbit coupling velocity times sigma z times momentum. What does it mean? It means that depending on your spin being up or down relative to some Rashba direction. So, oops, see if I can fit Rashba between here and there. Rashba spin orbit coupling. If the spin is up or down, it'll have a shift up or shift down in energy. What is this direction? It's some effective electric field in the material that gives rise to some spin orbit coupling. So usually this wire is sitting on something, silicon nitride, silicon something semiconducting or other. And between that and the material properties, there's an effective direction which gives you this coupling. So this should be thought of sigma vectors of this coupling. Now, why is it good? It's good because instead of having this parabola, right, you split into two parabolas. This is momentum and energy. And now once you add a magnetic field in a direction that's perpendicular to the Rashba direction, what can that do? It mixes the two spin directions. And in these two spin directions, this would be the down, and this would be the up parabola. So what can a magnetic field do if it's pointing in the sigma x? It can mix the two spins, right? Does it matter over in this momentum? No, because I don't even have board to draw the other energy up here, right? So you have to have like a really kick-ass magnetic field to actually mix this spin down with this spin up over here, right? But where would it matter? See people pointing at the no gap. Yes, here you have degeneracy, if this will split. If that will happen, this will become an avoided crossing. And if your chemical potential is somewhere in that gap, it looks as if you have a single fermionic flavor. Right? There's a right mover over here. There's a left mover over here. They have different spins, spin down and spin up. But there's still a single flavor. Actually, it's great that they have opposite spins. Because next, we can take this poor wire and put it next to some regular S-wave superconductor. And what S-wave superconductors know how to do best is pair spin down electrons going one way with spin up electrons going the other way. That's great. That will create a P-wave superconductor living here. In practice, we want to somehow Bogoliubov-Dejean this equation, right? Which we can do. So in the same vein of what we did last time with this Liang-Fu way of writing the spinner, the Nambu spinner, I'll put a tau z over here. I'll let B sigma extend, and I'll let the pairing delta x. So I was involved in the work that suggested that was led by Yuval Oreg, and it was Yuval, myself, and Felix von Oppen. And in parallel, and actually a few weeks before us on the archive, there was exactly the same construction put forward by Roman Luchin, Sing Jae Sao, and Shankar Kusama. And this was picked up. This idea was picked up actually by Leo Kopenhagen, who very quickly thereafter made an experiment with indium antimonide to actually show the peak of density of states corresponding to a Majorana. Now, I don't have a whole lot of time to discuss this on Newtonian. It's a fun one. I feel personally attached to it. There are several things that I suggest that you might want to do, and once I'll distribute my notes, you can see that some of it is done in the notes. You can start asking about when the topological phase occurs. In the sense that, what do we need for a topological phase? We need a P-wave superconductor, right? So we want this gap to be open due to a magnetic field, right? And we want the gap over a large momentum due to superconductivity. There could be a situation in which there will be a gap here and a gap here because of superconductivity both. Is that topological? It's not. Why? There will be like two copies of P-wave superconductors, one on top of the other. So that's like a non-topological thing. Back to the S-wave. Let me do a little bit of that. So what I wanted,
Quick question.
Yeah.
The V and the delta yesterday played a very specific role in your diagram when you projected down to the subspace of the operators and at magnitude of V equal to magnitude of delta. Are those the same objects in this case?
Yes. So let me go through it a little bit. So yesterday, we just had the same Hamiltonian, but without this. And then all physics were topological, and I was just saying, depending on whether you B dominated or delta dominated, you get a paramagnet or a superconductor, but the domain wall will contain a fermion, Majorana fermion. This is not true here. It's a wire, it's not a topological object. You can force it to have a topological phase, but it only happens at the range of parameters. So let's figure out the range of parameters. And it's not so hard given what we did yesterday. Any other questions? It's a bit of a rough start, so stop me with questions. And if you want to ask questions for 10 minutes ago, please go ahead. Anything else? You're following? All right, so if you want to do a phase diagram, let me lower the board a little bit and just say that this gap, this pairing, will open a superconducting gap with a high momentum. Can you see why? Do you understand the statement? It's just because at high momentum you will just have you will basically just have this p squared times tau z, that's delta tau x. That's just like a regular BDG equation for a superconductor. It'll open a gap at the chemical potential. Ah, that's what I'm forgetting. I knew I forgot something. Minus chemical potential. Now everything is good with one. The chemical potential will decide where we are in this. And just to emphasize the point, the chemical potential is up in energy. You'll get two gaps, one over here and one over in the middle. Okay? This will be a superconducting gap next to the chemical potential. But let's concentrate on this region. If you concentrate on this region, which piece of this Hamiltonian can I neglect? P squared, right? Let's neglect it. And then, lo and behold, you get something that's very similar to what we had yesterday. And in fact, let's look specifically at momentum equals 0. Yeah, let's even remove that and just look at the gap at 0. Is that okay? So if I do that, I can again square the Hamiltonian. This time,
So Gil,
yeah.
if you're looking at momentum equal to 0, then you can also get into like a BEC with the chemical potential, because now you're not pairing at the at finite momentum, right?
No. At P equals 0.
You're going
So the
more
point is-
into a
no.
BEC regime.
That's right. So this is not completely right in the sense that what the statement about BEC is not completely right, because once you have a chemical potential over here, then you actually want to
Oh, you are fixing your chemical potential over there? Okay.
Yeah. If you have a chemical potential over here, you'll have a regularized wave because of the combination of this guy and that guy. Right. So if I take this Hamiltonian and P equals 0, well, if I'm not working with this board yet, I can just do this here. Can you see here? So if I look at this HPDG at P equals 0 and square it, what do I get? I get mu squared from here, right? I get v squared from here. I get delta squared. But then I have another piece, which is b sigma x, 2b sigma x times delta tau x plus minus mu tau z, right? But this is like a magnetic field, right? That has the value of delta squared plus mu squared. That's multiplying the v. So if you think about this, not the sigma x tau x that we had yesterday, but sigma x times some shifted tau, we'll get the same kind of privilege of writing the plus minus for this operator, and then we're struggling with what to erase. Maybe I can erase this half of the dispersion. Is that okay?
What is the purpose of a squared Hamiltonian? I'm missing.
I want to see what. It's a good question. I want to see when this gap closes. Right? So since I need this, let me just go to the top board. Give this equation below. Then what I get is an a squared.
You can push that board all the way up.
I can push it up. That's great. It's coming. Okay, now my problems are again solved. So a squared is essentially so mu squared plus delta squared plus b squared plus some operator sigma x times tau, let me just call it tau hat, it's some combination of tau x and tau z times square root of delta squared plus mu squared times b. Right, that's clearly the magnitude of this operator. And you can multiply it with some polymetrics and some shifted direction. I would bet you anything this computes with the Hamiltonian. And then it means that the energy at momentum equals 0 is plus minus u squared plus delta squared square root plus minus b. This is what I wanted to achieve. What do you see from here? Before we had a competition between delta and b, right? If delta were bigger than b, then we knew that we had superconductivity. If b was bigger than delta, we had a paramagnet. Here we see that when we put in the chemical potential, I get another piece modifying the delta that pushes us towards triviality. Now, so we can draw a phase diagram, and instead of having b and delta, let's have b and mu squared plus delta squared square root. And now we can have the same kind of cross. If b is large, then we have a paramagnet at zero momentum, right? But a paramagnet at zero momentum doesn't do anything to the superconductor at high momentum. So this is the p wave superconductor. And only these lines matter in this phase diagram, right? Not the axis lines. If the mu squared plus delta squared is stronger, what do we get? Get a superconductor near momentum 0. We have another one near momentum k Fermi or whatever. So this would be the trivial superconductor. It's not exactly it's not the simple S wave as you're used to it, because the spin-orbit coupling breaks the spin symmetry, the rotational symmetry. Now, I have to admit that back when we did this work, we were pretty confused as to which is the topological phase and which is not. Because having this extra wings in the dispersion completely reverse things. Now, so this is how you would get a p-wave superconductor in wires, right? And it also shows you how you can control the phase of the wire with the chemical potential. So if you look at the stop diagram, and in your mind's eye, because there's no way I can fit it into the board, you also add like a keyboard of gates that can control the chemical potential locally. You can see how those gates can plunge the wire in and out of the topological phase. And at the edges of the topological phase, at the edges of the p-wave superconductor, as you go from p-wave to trivial, or from p-wave to nothing, because the wire can be cut, you'll have Majoranas. That's where you have the Majoranas ones. In terms of parameters, just for those of you who are somewhat experimentally inclined, you can find that this V that I have up there is around 3 times 10 to the 4 meters per second for indium antimonide. And indium antimonide is really good material because it has a G factor, namely the ratio, the ratio between the energy, the Zeeman energy of an electron and the Zeeman energy that you would ascribe to this term. So if an electron G is 2, for this material, can you guess? Anything? Any numbers? 50. What?
100.
50. Yeah, good guess. It's large. What's the intuition behind it being large? See this antimonide up there? Like, both the indium and antimonide, I think they sit right next to each other in the periodic table and pretty high up on the 50s. So the higher the number, the bigger the nucleus, bigger the local electric field is. And the bigger the spin-orbit coupling. And the G factor is also likely to be large. Right, so those are the numbers. They also dictate the gaps that you will get in the actual wire. And Leo Kopenhagen's experiment from 2012 came up with gaps on the order of fractions of a Kelvin with magnetic fields of 0.1 Tesla. Yep.
Do you worry about fluctuation effects killing the superconductivity in these low-dimensional systems?
Yeah, so the superconductor that gives the proximity is not a low-dimensional object. It's about superconductor.
And that controls everything.
That controls everything. That said, there's subtle physics that has to do with the electron going in and out of the superconductor, which renormalizes the velocity that determines the localization length of the Majoranas. So that was something that was clarified by Glasman and Van Oppen recently. I mean, the Majoranas are more localized on these wires than you would expect. That was the reason for some early skepticism. But it seems to be clarified by the fact that the electrons spend some of the time in the superconductor that renormalizes their velocity. And the velocity, the length in the velocity, determines the localization of the Majorana. And I can comment more about this later if we want to. All right, I didn't want to say so much about wires, but like I said, it's close to my heart, so once I start, it's very hard to finish. Questions on this?
Could you explain again how do you determine something is P-wave or not?
So roughly speaking, you have single flavor fermions, P-wave. Even flavor, not P-wave. But there is an exercise that I do in the notes, and I wanted to do it yesterday, but I don't want to do it today, which is look at the limit of B large and mu large. What would that do? If you have B large, you see this gap over here that I did for the unpaired gas? That gas is going to grow and grow and grow. And in the end, you just have one parabola here, with the other parabola way up at 2b, right? You can expand the Hamiltonian in terms of just the down electrons plus some correction. Some small correction. Why is that correction there? That correction is there because of the spin-orbit coupling. Right? The spin-orbit coupling does not commute with the magnetic field. It's going to tilt the spin a little bit, but really just a little bit. You can rewrite this Hamiltonian in terms of projected into this sector, and then you immediately find the P-wave superconductor Hamiltonian diagonal. But I'll let you do this exercise if you want. It's kind of fun, second order perturbation theory and all that. Other questions?
Because you made such a authoritative and powerful statement, single species of fermion P-wave, even if there is somebody in the audience who's wondering why that is, they may not have courage to ask. So maybe you can add half a sentence.
Sure. So if you have single flavor fermions, so those are fermions that still have to obey antisymmetry upon braiding, right? Upon exchange, right? That means that but the only quantum number that describes those single flavor fermions would be momentum. So if you exchange two of these flavorless electrons, single flavor electrons, then you have to exchange their momentum. And upon exchange of momentum, you have to have a minus sign introduced. But upon exchange of momentum is like upon exchange of momentum, you also take the pairing, which is pairing momentum plus with momentum minus, and change it into momentum minus to momentum plus, right? So that pairing function will have to be odd in momentum. But the pairing function depends on momentum. It will have to be proportional to momentum, such that it switches sign on momentum. And that would be the P-wave. Is that a satisfying explanation? And do you see that I was myself confused about this for years and years? Anything else on your mind?
So basically your schematics is very general. You just need some kind of parabolic band with strong spin-orbit coupling. So why are these materials special? So
They make wires.
oh, that's the only reason.
Yeah, people know how to make wires out of them.
Uh-huh.
They make this nice, like what's it called? There's this nice term for this, like self-created, self-constructing wires. Like you get your MB machine going, and it'll produce like this nice self-assemble wires. And so there's some papers out there in the archive from the usual suspects showing how you can even get like junctions of those wires if you get your conditions right, and the wires come out to be very clean. And indium antimonide was used in Copenhagen experiment. Monty Heidman was the second to do something like this, and he used indium arsenide wires, so that's what his fab facility was doing best. There could be others, but you need to satisfy some chemical conditions, I think, for this to happen. I should say, there's still controversy as to whether we have seen Majoranas or not. But I think I don't want to go through the experimental evidence because I wanted to go to this nanobellion, to the nanobellion chapter of my presentation. But you're welcome to look at some of the early papers, and you can see that as for Leo Copenhagen's experiment, as you tune the magnetic field and induce a phase transition, he sees a mode appears in the density of states that gets stuck at 0 for a big range of magnetic fields. Now, if you change a magnetic field and you produce like an Andreev bound state or Andreev state at 0 energy and it stays at 0 energy, you have to spend a lot of time explaining why it's there if it's not Majorana. And there might be other explanations. So far we have ruled out all of them, but it doesn't rule out the possibility that tomorrow somebody will come up with another compelling explanation. But that compelling explanation would be an interesting piece of physics, because it would be another generic mechanism for pinning an Andreev state to 0, two Andreev states to 0. If it were just one Andreev state pins at 0, what would it be? Just single state, be Majorana. So if it's not a Majorana, it means there are two of them, and for some reason they don't talk to each other for a long range of parameters. Okay?
So has the experiment been done at both edges to establish that you see it here and here?
I think that's the challenge. I think the Majorana that they see is probably has the endpoint. So as of a year ago, what I heard anecdotally is that experiment was not done yet, or was not successfully done yet, which indicates that you have a second Majorana that's sitting not close to the edge of the wire, but somewhere in the middle.
No, even if it's in the middle, then there must be another.
There must be another one, but the question is whether it will be next to some tunneling tip. You would want to see the density of states of those Majoranas correlated on the two sides, right? But if the second tunneling tip, or the second tunneling connection, right, it's like a tunneling junction, basically.
Yeah.
If it's not next to the second Majorana, then may or may not work. And then you can imagine that the wire fractures into several domains of pure superconductor, and then you won't see exactly the same Majorana. I mean, what you really want to do is something along the lines of noise measurements, and see how tunneling on the right, tunneling on the left are correlated. And there's a big chunk of physics that talks about what happens when you tunnel Cooper pairs to a pure superconductor with Majoranas, and what happens when you tunnel single spins through that. And there's various noise correlations that are very surprising, I think. Again, the usual suspects have worked it out. Binnaker, Oreg, I think Pete Brower was involved in things like that too. And there's a lot of physics that has to do with disorder in this wire. Some of it harks back to random singlet phases. Some of it has to do with Anderson localization. Again, that was worked out by the Berlin group at the, in the broadest way. Other questions? Another billion? Go, yeah, last question.
So why is this rush bar spin orbit dominant? Are there like Dressel House, some other spin orbit coupling?
Yeah, so Dressel House is dependent on momentum cubed, right? But here you only have one momentum that's a parameter. So, the Dressel House would be important in extended semiconducting devices. So in 2 dimensions, there are proposals to use that preceded this that suggested using a combination of Rashba and Dressel House, or even just Dressel House, to stabilize a POA superconductor and then use vortices in that POA superconductor in 2 dimensions to localize Majoranas. And the important part was that that way you could have your magnetic field that opens the gap parallel to the layer, and that way you won't necessarily destroy superconductivity. So the idea was having a 2-deck semiconductor with Dresselhaus, having a superconductor somehow above it or below, and then you want to open it, again, there's a dispersion like this, you want to open a gap at 0 momentum, and just keep the high momentum pairing intact, but not the low momentum pairing. For that you need a magnetic field. Naively, you would have to have it perpendicular. But with the Rashba interaction, you can have it parallel. Not with the Rashba, with the Dresselhaus. Now, I have to admit that I went back and tried to read the Dresselhaus paper on Dresselhaus interactions. And I couldn't. It was too hard. So I know from later books about what Dresselhaus is. And my naive understanding is that in this wire, Dresselhaus and Rashba mix. Because p cubed is like p squared in the other directions times the p along the direction. Right? So it all kind of goes into this generic area of Rashba. That's my understanding. Okay, should we go to another meeting? All right. I wasn't really prepared to have such an elaborate discussion of the wires, but like I said, self-control is not very easy for me. All right, but non-abelianness. So non-abelian nature. Now, again, what I want to show you is practical non-abelian physics of Majorana, as much as I can. And again, coming into this field, I was confused by this non-abelian nature of Majoranas. And it took a while until I understood how to actually work with the concepts of braiding and exchange of Majoranas. And I wanted to share some of those insights with you. So the first thing is, why are Majoranas non-abelian? Or how do you see that they're non-abelian? Let me just write how. And think about a two-dimensional phase that supports Majoranas. If you want to think about wires are not two-dimensional, but you can make networks out of them. In particular, you can exchange and braid and do whatever you want in a T-junction of topological wires. So instead of telling you how that goes, with one comment that I forgot to say before, the way they would go with the T-junction to braid Majoranas, you would use the keyboard of gates to move Majoranas around. And you can think of doing the same way that you do a white one in a car. You can get two Majoranas to braid themselves. And if you can't visualize it by the end of the talk, ask me, and I'll show you. That's something that Jason and Alicia, I think, clarified. But let's just think about a continuous two-dimensional topological phase and have two Majoranas. Now, if the Majoranas were regular fermions, just two electrons, you take the electrons and exchange them. What would happen to the wave function? What? Picks up the minus sign, right? We want to figure out what happens to this Majoranas when we exchange them. So first of all, let's recall that two Majoranas give rise to two fermionic states, right? Let's call 1, 0. Actually, you could have called 1, 1, then the sentence would sound a little better. But let's stick with 0. And then we can have another one called 1, oh, there we go. How would we construct it? It needs to be some kind of a C dagger over this one. How do we make a C dagger out of these babies? Gamma I plus gamma A plus I gamma B. Apply to 0. Is that all?
1 root 2.
Okay, Majoranas have a funny normalization. Not root 2, but 2. Why? Because each one is like C plus C dagger, right? It's again one of the confusing things. So it's 2 here. Right. Now, yeah. If that's the case, Okay, so let's remember this. And now, what happens when you exchange Majoranas was clarified, I think, the best by Ivanov, which was, I think, also around 2001. And what was said is the following. Each Majorana carries a bench cut. Actually, each fermion kind of carries a bench cut. And the point is that whenever the fermions cross each other's bench cuts, they get slapped with a minus sign. But with Majoranas, the following thing happens. So if we exchange these two Majoranas, let's see in detail what happens. So let me modify my animation on the board and say that to exchange gamma A and gamma B, I'm going to take gamma A all the way to here, and then just shift things back into the frame. Are you okay with that? Okay, so if, if that happens, did gamma B cross gamma A's bench cut? No. But gamma A crossed gamma B's bench cut, right? So in the way of gamma A to become gamma B, it gets that with a minus sign. Gamma B just stays put, right? But when gamma A gets to here, gamma B takes the role of gamma A. Right? It's the one to the left. Now, something must happen to 0. I don't know what it is. I don't know how to calculate it. I don't want to calculate it. But what we need to find out is what happens to 1 relative to 0. Now, because 0 appears here and 0 appears here, we can avoid calculating what happens to the 0 and just calculate what happens to this operator. With this, we have gamma A plus I gamma B going to, let's do this carefully, minus gamma B plus I gamma A, right? Let me pull I outside, and I get this. Which means that 0 went maybe to some phase times 0, but let's drop that phase. But 1 went to I times 1. Right? But this is the operator that created, that raised 1 from 0. We get an extra I. What happens if we then take this gamma A back to its original place? Nada. So we get a minus 1. This behavior is kind of like half a fermion behavior. Upon exchange, you get an I, which is the square root of minus 1. Upon another exchange, you get the full minus 1. So this is an exchange. Exchange. And if you want in the notebooks, write what happens for a full braid, which would be I squared. So that's kind of cool because what this means is that if you're looking at the state with filling n, either 0 or 1, it goes to I to the power of n times itself. Now, the Majoranas are not going to be close to each other throughout the process, so the Hamiltonian is always 0. Okay? And but this exchange gives you a phase that depends on the state of the Majoranas. So the statement is that, well, A, you can write information into these two Majoranas, into the state 0 and 1. Those 0 and 1 have a topological degeneracy, namely, the splitting between those two states is exponentially smaller than the size of the system. You cannot locally measure that state. And you can carry out quantum gates on that state just by braiding. But questions so far?
I mean, so this procedure, you can't do this in 1D.
What?
I mean, I thought you had this two-dimensional structure
Yeah.
to do this braiding operation.
So you can do it in a T-junction. You curious to see how it goes?
Sure.
So in a T-junction, So really imagine, oh, you live in New York, you're probably not driving. Yeah, because you should really imagine doing a Y turn. So if you have a T-junction, right, made out of these wires, you can decide which part is topological and which part is not, right? Let's start with this guy, topological. Okay? Then you would have two Majoranas over here. Now what you want to do is exchange them. So little by little, you bring this Majorana over to here by making this wire non-topological, non-topological, non-topological until this half is non-topological and this half is. So then you'll have a Majorana here and Majorana here. So let's erase this Majorana from here. Then you bring it down by making this piece topological, while this piece is not. Okay? Then you can take this and by the same process, just bring it to here. And then bring that to here. And you see why I'm saying Y junction, right? Sorry, Y turn. It's like going like this, and like that, and then you turn your car. Yeah.
There's something I don't like about this argument about, or at least the words you're saying of the phase depends upon the state. Because isn't that ordinarily the case? If I, imagine I have two little tweezers that can hold a fermion. So I have a fermionic state there, and they are empty.
Yeah.
If I exchange these two things, I don't get a phase.
You get a -1, well,
If
you
they're
exchange-
empty, there's nothing there.
If you're empty, that's right.
It's empty, right? But if there's a fermion, and if there's a fermion
No,
in each
but
of them,
so what I
however,
would calculate
I do.
is again the phase relative between 0 and 1, right? Between the full and empty. So you're discussing one many-body state, empty and empty.
Yeah.
And then you want to look at the relative phase between the empty, full empty, or full.
Yeah, so I mean, if
The
you
relative phase
exchange full empty, that doesn't do anything.
No.
Right. So it's,
Right.
it's a full versus empty, and I get a
Or
I
full
get-
versus all the others, yes.
I get a -1 when I do full. I get none
Okay.
when I empty.
That's right.
And so, what's the difference between that and getting a phase?
Yeah, that's an untrivial phase.
Right. So exactly. So the fact that it's I instead of -1 is the interesting thing, not the fact that you get it only if you are in one of these two states.
Yes. Also, yes, I think, let me show you the next thing and then you get it. Because this I, it's not just that, it's also the fact that you can entangle things better this way.
Yeah, absolutely. No, I'm not objecting
show you how this
at all. I'm
argument
just
is
objecting to the
entanglement.
argument.
Yeah. Yeah, I think it's the fact, it's not so much the fact, so with two electrons, I don't want to get too much into this, but with two electrons, all the phases that you get will be trivial, in a way. The thing that's not trivial here is that you have only a single fermionic state between them. And the fact that you can, so maybe part of the magic is that you can still do this quantum gates with this braiding without actually knowing whether you're full or empty. In your case, I can say whether you're full or empty by a local measurement. That's another piece of magic. But I think I don't have a canned answer to this question, except that these you can entangle with these gates in a way that you cannot fermions. And let me show you that next.
And there's another question over there.
Yes.
So is there a good physical reason, like more intuitive reason, as to why you can't really have like two exchange operations? You either take, gamma A below gamma B or gamma A above gamma B. You get different, phase factors depending on which one you do.
You get the same thing.
But one of them you get gamma A goes to minus gamma B, one of them you get gamma B goes to minus gamma A.
Check it, you get the same thing.
Because there's only two. Once you have more, then you can start braiding. With two, you can always undo it.
Yeah. I mean, check
Because he
it.
did it with two.
That's why, you notice that, usually I try to be careful, but when I did this, I didn't try to be careful. Like, I could have spent like 10 minutes on the board trying to figure out whether it's A going through the line of B or B going through the line of A. Is it A that gets the phase or is it B that gets the phase? I didn't think about it because it doesn't matter. But let's do, this is, yeah, but Una raised a good point. This cannot be a qubit. Because it has different parities. The qubit states are encoded into different parities. That's not good. That's something that you can measure from the outside of this thing. So if you want a qubit, you want to make it from 4 Majoranas. And let's see how you process information with a qubit of 4 Majoranas. So let me make a bigger diagram for 4 Majoranas, but it'll have the same kind of thing. Gamma A minus, gamma A plus. Those will be 2 Majoranas giving rise to 1 fermionic state. I'm drawing them close to each other, but they don't have to be close to each other. Let's think about, in the same system, you can have another set of 2 Majoranas. This gives rise to how many fermionic states? 2, right? In that case, I can write the Hilbert space in terms of the 2 occupations, actually the same system that Eric was writing. And here, we can take out of these 4 states and use 2 states for a qubit, with the 2 states having the same parity, right? Those states can be, for instance, 0A, 0B, and 1A, 1B. What do I mean by this? If you look at the A Majoranas, you can ask, are they odd parity, even parity? And same for B Majoranas, and this articulates 2 of the 4 states. What are the other 2? 0, 1, 1, 0, right? Now, if you take these 2 and braid them, it's exactly what we did up there, right? So now let me give you a headache. What happens if you braid these babies? That basis is not good for braiding that way, right? Let's see how we calculate that. You up for that? And this is really how you can, this is really how the braiding actually gives rise to this gate operations. Okay, so let me just do a little bit of algebra gymnastics. So let's recall that CA would be gamma A minus plus I gamma A plus, say. CB would be gamma B minus plus I gamma B plus. I could have had some other combination, but all of them would work. Now, CA operating on this thing, what would you get? So CA, the destruction, the annihilation operator of the A state, what do you get over here? 0, because there's 0 here. Right, so it annihilates this state. CB on that, 0, right? CA dagger, these guys, 0. 0. 1 plus 1 is 0, of course. Now, if I want to do this braid, I don't care so much about what the occupation in A is and what the occupation in B is. But I really want to care about what's the occupation in the plus fermion is, right? Then, I would like to write down additional operator, C plus and C minus, right? C plus would be gamma A plus I gamma A minus. Sorry, gamma B plus. There you go. And that can work. I think that's enough for what we need, and we can work with that. Because what is this? And there are halves everywhere that I didn't write, but you're free to write them in your notes. Maybe you can even write it like this. It's very elegant. I can write C plus in terms of these guys, right? So let's see. So C plus would be, so I want CA. That would give me gamma A plus over here, right? So let's prepare with the minus I in front. Right, so CA will give me gamma A plus. I can get gamma B plus from here, right? For that reason, I need to subtract CA dagger and CB dagger. Right? Now, from A, I got 1 gamma A plus. From B, I got 1 gamma B plus. From CA dagger, I get another gamma A plus, right? And from CB dagger, then another gamma B plus. So I need to divide by 2.
I think you lost some I's on your B's.
The CP needs to be outside the I.
The CB needs to be outside the I. No, I don't think so. Because CA dagger, we just have a minus sign here. Right? Does it make sense? You want me to go through it? Let's just test it. So CA minus CA dagger is gamma A minus gamma A minus, because this doesn't change. And then plus I gamma A plus, then minus I gamma A plus. So I think it's okay.
The A is correct. The B's you need not.
an I.
The B's need an I?
Because
Your
it's I,
definition is
I
C
gamma B
plus.
plus in the C plus.
I gamma
In the C
B.
plus, it's I gamma B.
Absolutely. Thank you. Thank you. Yes. And that is, of course, important. I wanted to construct this because this will allow me to tell what those states are in terms of that filling, right? How do I do that? Well, what do you think 0, 0 is, baby? What could it be in terms of the plus minus? What's the parity of the state? It's even, right? So the only thing it could be is a combination of even and odd, right? For plus minus. What is alpha? I have no idea. Let's calculate it. Similarly, for 1, 1, there will be another state like this with another number here, beta. Whatever it is, it should be orthogonal to this state. You see what I'm doing here? How can we find what this alpha is? Any ideas?
Add CA on it. CACB on it.
Have what?
Add CACB on it.
Okay, so CB on it will give you 0, right? That's exactly right. Now, if you add CB on this, or CA, you should have 0, right? And now I literally realized that I did the wrong kind of conversion, because really what you want is you want CB in terms of C plus and C minus. We can very quickly recover because of the duality between the plus and minus and A and B. So let's write it here. So CB in this case would be C plus I, C minus C plus dagger minus I, C minus dagger. Probably a half. And probably minus here. Yep. Now, if I take the CB and operate over here, I should get 0, right? And let's see what we get. So over here I get C plus minus C plus dagger, right? So let's do it one by one. So C plus operating on this gives me 0, right? Operating on that gives me 0, 1, right? 0 plus 1 minus times alpha. right? Now, let's see. I can go on doing this calculation, but not everything will give me a 0, 1, right? So let's see what else gives me a 0, 1. And make sure that whatever we get in the end is 0. So the other thing that will give me 0, 1 would be a C minus dagger, right? On this guy, right? That guy doesn't have an alpha. It's good. But C, so let's see, so C plus dagger, right? No, C minus dagger is what we wanted. C minus dagger has an I. There will be other things, but they won't be 0, 1. Right? That's the only contribution of 0, 1. You can check that they would have the same kind of combination, but this tells us that alpha equals what? Minus I. There you go. But now I'm being a little suspicious actually, so let me just check my notes for a second. Yeah, so let's I have a feeling that I got this I wrong, but we can check it later. I think ultimately there shouldn't be an I there. But with the lateness of the time, let's leave it for later to check. Well, let's do this quickly now. So let's do it really quickly and see that it actually operates, that it actually works. So we want C plus, right? Sorry, we want CB, which is this one. Gamma B minus plus I gamma B plus. And we wanted to use C plus, which is gamma A plus I gamma B plus, and C minus, which is gamma A minus plus I gamma B minus, right? Okay, now I want gamma B. So I want CB, gamma B minus plus I gamma B plus. Gamma B minus starts with minus I C minus. This gives me this, right? Now I have this guy that I need to take care of. So I need to subtract C minus dagger, right? And then I need another I of gamma B plus. But gamma B plus is C plus minus C plus dagger, right? But divided by I. Right?
Oh, there's in the bracket there is no I in front of the CB actually.
What?
C to the right and then to the left. There, and then there's even to the right.
What?
Even to the right, and then I think there's no I in the CB there.
Here?
Because CB minus CB dagger.
Has an I already. Wait, so let's see. C minus minus C minus dagger, giving me the gamma B minus, right? Sorry, no. What I wanted here is, gamma B minus. And that's what this gives me, right? C minus minus C minus dagger. And there's a minus I because it comes with an I. And then C plus minus C plus dagger. again has this I over here, right? So I think,
It's correct.
what?
It's correct.
That's correct, yeah. Okay, so let's go with this, and then we have the answer that here we have a plus I, right? And then, right, actually, this is okay. I'm not sure why I'm getting confused with this late hour. Are you okay with the calculation? You saw it was done? You saw it was done twice? All right, so we erase it. And then, if we know this, then we know that 0A, 0B is, let me adopt my answer. So we have minus I, 1, 1. 1A, 1B has to be the thing orthogonal to that, right? Which I think is this, no? And then I'm okay. It's very confusing to multiply these two vectors together because you have to complex conjugate and everything, but it'll give you 1 plus I squared, right? Okay, and now we break. Let's break this guy. Let's replace, I erased the diagram. So let me do this again over here. Gamma A minus was here, gamma A plus was here, gamma B plus was here, gamma B minus was here. You agree? And I want to break these babies, right? So that means that if you break this, what do you get? 0A, 0B goes to what? So it started off like this. So what do I want to do? I want to exchange. I want to do a full break. I want to do a full break. Okay, 0, 0. What happens to it? Stay 0, 0 or not? Stays, right? What about 1, 1? So we break. We do one exchange and then we do another. What?
There's a minus 1 factor.
There's a minus 1 factor. So this becomes a plus. Which state is it? 1, 1. That was a lot of work. We're getting this fact. But it works, right? I don't know why I was doubting myself before. Trust yourself, that's the lesson. It works, even without any notes. Okay, good. Right, so we get 1, 1 upon break. What happens with an exchange? Such an exchange. It won't be a minus, right? It would just be an I. That would be like a rotation by 45 degrees. So by 90 degrees. In the sense that if we do, this was an exchange, a break, sorry, this was a break, and now for an exchange, what you would get is that 0, 0 of A and B will go to superposition. 0, 0 AB plus 1, 1 AB. And you can show that. There will be a coefficient in front, like it will be like 1 plus I in front. But you can calculate it. Right, so exchange does this, break does this. What about universal topological quantum computing? So there's a question, we can end, I can tell you what I was supposed to say, or you can take another 5 minutes and I can give you the function of topological or universal quantum computing.
Take your 5 minutes.
5 minutes, okay? With time dilation? All right, So you can do this. And now there's a question, can you build a quantum computer out of this? It looks suggestive. So what do we need for a quantum computer? Do you need that board? I'm not sure. Universal quantum computer. So there's a theorem that says, let me just keep this here, I may need it. There's a theorem that says that if you want to build a universal quantum computer, you need a bunch of things. Those things are the Clifford's gate. So on the qubit, you want to have the Hadamard gate. You want to have a pi over 2 rotation, or pi over 4 gate, namely, let's just call it P because P is the first letter in pi, so it's very helpful. And you want a C naught. C naught is an interacting gate. So I need the space of 2 qubits for it. But the idea is like if one qubit is 0, nothing happens. If one qubit is 1, then the other qubit gets shifted. This is not enough. Any classical computer can simulate this. This is my understanding. However, if you add to that a T gate, which is 1 e to the I pi over 4, then you're in business. Okay, this you can do with Majoranas with the braiding. You can prove to yourself that you can do that. This, you don't even need to prove to yourself that you can do it. It's right here. Right, e to the pi over 4. So e to the I pi over 2, last time I checked, is just I. But don't trust me today. Pi over 4 is a problem. It's like, you know, there's those jokes about you can't be half pregnant. So you can't be half exchange. But that's what you need. You need a half exchange. You need to go and exchange and then stop. This is missing from Majoranas. However, so in the last couple of years, last 3 years, together with Yuval Oreg and Thorsten Karzig and Mike Friedman, we figured out how we can make this gate protected for a machine that doesn't have high frequency noise. So you have a machine that has Majoranas, and it's stable, doesn't change in time. Then we can give an exponentially precise gate like this. I can show you quickly how it goes, and I think I find it very interesting to see how this Majorana engineering happens in practice. So I won't derive anything, I'll just show you the flavor, and that should take me for the rest of the 5 minutes. So the way you actually, one way of thinking about manipulating Majoranas is to think about what Penneker suggested, which is a Y setup. So what Penneker suggested, I think around 10 years ago, is have your Majoranas not in a row, but in a Y. So put gamma x here, gamma y here, gamma z here, and gamma 0 here. Why do you do that? Well, with superconducting wires, you can actually control the bond between gamma 0 and the gamma in the environment with exponential precision. You can make it either 0 or something. So you can make a switch of either being 0, like really 0, or something finite. So you can always make one of the bonds much smaller than the others. And that's a reflection of the topological protection in the sense that to make something 0, you just take the Majoranas very far away from each other, in a sense, and you can do that. Technically speaking, you have some kind of a squid here, and the coupling over here, and over here, and over here is controlled exponentially by some big ratio between some Josephson energy and charging energy times some cosine of a phase. So it's like exponential of something that's very large. that could be tuned to 0 to get something finite, but whenever this is non-zero, you'll get this to be 0, right? The Hamiltonian for this is just written as I gamma 0 times delta dot gamma. I'm just thinking about like a vector, gamma x, gamma y, gamma z. It's an operator. And delta is those three numbers arranged as a vector. The nice thing about this is that you can braid here. Suppose you want to braid between gamma x and gamma y. Think about it like a clock. Start off with this bond being very large, and these bonds non-existent. These are Majoranas bonds, right? They don't talk to each other. Here, you have a fermionic state that has a gap. Actually, the value of the gap would be the magnitude of delta. Now, you want to take these two and replace them. What you need to do is wind the clock. Take this bond and make it into a superposition of this bond and that bond. Once you're done, what happened? Gamma x stay put. You have a gap state over here, and the free Majorana over here, right? So you end up with this situation. This stayed gamma x, but whatever was here has to show up here because of the adiabatic continuation, the adiabatic evolution. So this is where gamma z is going to end up, and this is where gamma y is going to end up. And then you can see as I wind the clock over to here, and I wind it back over to here, I'll end up with these two replaced. You see this? In terms of the phase that you would get, it is actually a Berry phase. So if you have x, y, and z, what we did, this is delta x, delta y, delta z, we went in a cycle that started off with delta z large, right? Went to delta y large, went to delta x large, and back. It covered the Berry phase, which is d phi cosine theta. And if you calculate this for this, you'll get pi over 2. And this pi over 2 is basically pi over 2 from here to here. Cosine theta is 1 over here and 0 over here. Pi over 2 is this pi over 2. Namely I is e to that pi over 2. It's that pi over 2. It's good. How do you get a pi over 8? Pi over 8 gate. There's pi over 4 difference between the two states. Well, you just do a half, right? It won't work. It cannot. It's too simple. Of course it won't work, because you know how to make one of the deltas 0, right? But you have no idea how to make two of the deltas identical to each other. God knows what these deltas are doing when they're not 0. So in fact, instead of having this trajectory, you would have something like, well, something like this. And God knows what phase this will cover. That's where the protection goes away, right? There's a trick. And I don't know how many of you listened when you took numerical analysis, but there are those polynomials called Chebyshev. Remember them? How many of you remember them? Good people. Chebyshevs are magic polynomials to tell you that they can interpolate any function that has some continuity conditions with exponential accuracy. And if you don't know your Chebyshevs, I highly recommend them. They're much better than your Laguerres. And so Chebyshevs have a magic property. Well, first of all, what are they? There's this cosine and r cosine x. Sorry, there's no room for the Chebyshevs here. There we go. Which means that there's just some kind of an uncontrolled oscillation between -1 and 1. Everything is the same amplitude between 1 and -1. And they have other magic properties, like for instance, they have orthogonality not by integration, also by integration, but also by adding zeros. Namely, if you take, I'll write it down, this over here. So if you take sum over n for pix tjx, where the x ends are zeros of yet another Chebyshev. This thing is delta ij and then. Why am I saying this? Because you can do the following thing. If you don't know where your system goes in between, let me just draw this again. You can do the following. Go down, go a little bit sideways, go back up. Go down, go a little bit sideways, go back up. Go down, go a little bit sideways, go back up. Hopefully you average over there. No guarantee, right? Because really what you end up having is sum of errors, sum of delta n, times minus 1 to the n. What is this delta n? What error you garnered because your system is kind of copied. And the minus 1 because sometimes you go up and sometimes you go down. And this is the machine error. It's a function of the space. Of the phi that you go along. What do I want to say? I want to say take that machine error and expand it in Chebyshevs. So we have the sum over m. So delta is really a function of phi. Delta n is really delta of phi n. Expand it, roughly speaking, this is schematic. In terms of Chebyshevs, like this. AM will fall exponentially fast in M. Now, phi, you can choose the phi's however you want, right? You can use this relationship to make sure that all coefficients, so if you make n terms, big n terms, so 2n terms, one up, n down, and then up, you can take your 2n terms, choose them in such a way that this sum vanishes for all Chebyshev polynomials with m smaller than 2n. Now you just think about it as a number of equations, number of variables. You see that you can do it regardless. You're not guaranteed the solution, for it's not a linear system. But the solution does exist. And plus, you need another condition that says that the area that you want to cover here is half the quadrant. You can do that. And then you get accuracy. You can get accuracy for the gate that's delta alpha is proportional to A to n, which is exponentially small into n. There you go. We covered the exponential accuracy. Yeah, so I didn't give you any of the details of how you do it, but it's really just simple algebra. You take this, you put this in here, you change the order of sum, and that's it. So the ultimate statement is that you can actually make a topological quantum computer just for Majoranas, but this scheme would only work if you don't have high frequency noise. There's a bunch of other wrinkles about correcting other errors that may arise that can be corrected, but the one thing that you cannot correct is the machine actually changing faster than your motion. Okay, that's a good place to stop. A little late, I'm sorry. Questions?
All right. Let's first thank and we'll take a couple questions.
So, without having seen all the details, the one thing that perplexes me here is, what does the experimentalist or the technologist do? How do the Chebyshev expansion play a role in how they're deciding exactly how to implement these ups and downs.
Right. So this is something that you can calculate, kind of. So I didn't write it, but there's a formula for what the spines should be. Actually, they're the zeros of the next Chebyshev. And so the nice thing is that, so the concept over here is you have a computer that controls the Majorana machine, right? The computer is infinitely accurate. The Majorana machine, you have no idea what's in there. But if the computer gives the correct zeros, if the computer tells the machine what to do correctly, then the machine will obey this rule, that the error will be suppressed. So conceptually, that's the thing. Like, all the mistake is on the side of the machine, and you can see that as long as you provide the zeros infinitely accurately, then you're okay.
And what the machine is doing is moving in the strength of the bond space?
Yes, exactly.
Okay.
Exactly. I mean, practically speaking, there will be some tetron or hexagon construction with some quantum dots that change couplings.
And so there's some optimal trajectory in that bond space that guarantees the exponential accuracy.
Exactly. And you need to only define it in terms of the variables that you know. And then the Chebyshevs take care of the rest in the transition.
We have another question back there?
I had the same question.
Oh, okay.
So this T-gate seems more geometrical than topological. So is it actually just like holonomic quantum computing, not topological?
Yeah, that's so when we wrote this paper, we called it geometrically protected T-gate. But really, this exponential does arise from the topological protection in the following way. So we use the fact, in order to do this, you have to use some knowledge about the boundaries of your parameter space. And the boundaries are protected by the topology, namely, the topological nature of this machine tells you that it can be exponentially close to any one of the planes in this graph. But it is true that this gate is not topologically protected in the same way against temporal fluctuations. That's the problem of it. So yeah, if you do this, maybe you can call it geometrically. So I don't know, I'm not very good with like terming things. I got into a fight about whether something is topological or just topologically inspired just earlier this week with Pete Brower, so neither of us could come to a conclusion. But what I did want to say, I like this problem not just because I worked on it, but also because it's an example of how you can use tricks from numerical analysis or control theory to augment quantum computing protocols. Yeah.
And another, like, why is the P-gate even necessary then?
Why is the T-gate necessary?
Or P-gate?
The P-gate.
Because isn't that just two T-gates?
That's right.
Except it's easier to realize than square.
It was there for free.
Yeah. Yeah. I mean, I think so. The way I remember the Clifford is basically all the Pauli matrices plus the C naught plus the T-gate. Yeah, it's a good question, but it was, yeah. That's it. I think the left is enough for classical computing, and then you need an extra element. And this is not unique, by the way. There are other combinations.
Eva had a question.
So are there any other good ways to implement this fiber rates?
Yeah, so actually there are topologically protected ways. I think Meisam Barkeshli is, and I think also Shali and Shi are the primary culprits for that. That requires the construction of an array of Majoranas in a bilayer quantum Hall state that supports them, and some sequence of tailoring them inside the space between the layers. And I cannot reproduce the scheme on the board or during the next few minutes, but I think it comes under the name of genome construction. I think there are more advanced suggestions that arose.
There's also less advanced suggestion of using read-reside state.
So read-reside state, but that's like
that's universal.
But that's Fibonacci's.
Yes,
Yeah.
Fibonacci.
So I thought the question was about Majoranas.
Oh.
So more complicated non-abelian elements could give you universal quantum computing right away. Una is saying that in 12 fifths, right? in the
Because all of these they're all hard. So 12-fifth is really, really hard. But given that these genons hard, this sound hard, so in the legal
this you can do with wires. So this you can conceivably see done in 5 years. But yeah, so there's a quantum Hall state called 12-fifths. It's suspected that there's a read-reside state there that has Fibonacci anyons. Fibonacci anyons have, so Majoranas have dimension square root of 2. Fibonacci's have the magic number, square root of 5 plus 1 over 2. So their Hilbert space is 1.618 per particle. They're lovely. I recommend you reading about them. They're harder to realize. I don't know that there was a measurement of them yet. But yeah, there are a lot of works that go in that direction, more complicated than abelian states. They'll give you right away these things. And parafermions is another path.
Okay, with that, let's thank Gil.